Here we go. Here is your quiz review. Let's take a look at the heating graph of water, and let's mark it up. We're told that we have 27 grams of water at 40 degrees Celsius. Well, where would that be? That would be right here. Oh, about here. Okay. Between about a little bit below 50 degrees would be 40 degrees. So we're working with water. Let's see. And we want to make steam. So the first calculation, I'm going to call it A. Whoops, I'm not going to write there. I forgot. I have the entire width of the screen. So the first part of the heat calculation is what I'm going to call step A. It's where we are working with water and we're heating water, liquid water, from 40 degrees to 100 degrees. That way we can vaporize the water and start to make steam. So what do you need? If you have a change in temperature, then you can do a Q calculation. You see, to go from 40 degrees to 100 degrees is a change of 60 degrees Celsius. Let me just mark up the rest of the steps so you know where I'm going. Once you've reached 100 degrees, you can start to vaporize the water or convert it to steam or gas. After that, we aren't done yet. After that, we need to actually heat the steam, heat the gas, okay? So that's the third part of the calculation, the heat calculation. So let's finish this. Let's finish part A. You remember Q is equal to the mass times C times the change in temperature. Let's plug right in on the screen. 27 grams. C of water. Let's see. C of water, you have to choose your correct C value. It's 4.18 joules per gram degree Celsius change. What's the temperature change? 60 degrees Celsius. If you multiply this, you will get a joule quantity. Okay? Let's go to the next part, which is really a phase change calculation, calculation B. We now have a mixture, and we're starting to convert this liquid to gas. Now, we need to convert the 27 grams to moles. And we know that the molar mass of water or steam is 18 grams per mole. And what we get very conveniently here is 1.5 moles of water that's being converted to steam. What do we need to multiply that? We need to multiply that with the molar heat of vaporization. Now I'm going to round. It's 41 kilojoules per mole. Per 1 mole that you want to convert to steam. So we have 1.5 moles. Now, before we do anything else, remember, if we want to add it to quantity A, we need to convert this to joules. How do I do that? Let's see. 1 kilojoule is 1,000 joules. Essentially, I'm multiplying 1.5 moles by 41,000 joules per mole. Okay? That's part B, the vaporization step. Now it's in joules. The last part of the calculation, right here, I'm going to call it C, is where you take steam at 100 degrees Celsius and you superheat it to 120 degrees Celsius. Again, it's a Q calculation. It's the mass. The mass hasn't changed. It's just changed into steam now. It's 27 grams, but C of steam is quite a bit lower right here than C of water. And so I'm going to multiply it by 1.9 joules per gram degree Celsius. And then the change in temperature is right here. The change in temperature is 20 degrees Celsius. I'll put it right here. Okay, and Q, I will get a Q value for part C. So again, your strategy here is to mark up the curve and carefully look at whether you have a temperature change or whether you have a phase change or a change in state. I'm going to switch now to the second problem on the quiz, and that is, not that it's a problem, it's calculating the enthalpy of reaction using Hess's law. Here we go. Here we go. Here we go. Okay, screen sketch. So let's focus on this reaction. This is a highlighter. Let's see. Let's go with yellow. Okay. This is the reaction we're focusing on. And what we really want is we want to calculate this heat of reaction using Hess's law without actually doing the reaction. So what we're given is two related reactions, and I've asked you to number them 1 and 2, and then to look and compare 1 to the original and 2 to the original to decide what you're going to do to equation 1 and equation 2. Okay, so let's focus on something unique. Okay, in equation 1, well, first of all, both equations have NH3, both equations have O2, so we're not going to focus on those two quantities, and we're not going to focus in either equation on the H2O. All we're going to focus on is the 2N2. It's related, or we can use this enthalpy of reaction to solve for our unknown. Okay, so what we're doing is we're comparing equation 1 to the original, or the one we're trying to solve. Now notice equation 1 has 2N2, and it's a product, not a reactant. So that right away tells us that we are going to reverse reaction 1. We're going to rewrite it in reverse. How do you do that? And that's not all. That's not all, folks. We also need to divide that reaction by 2 or multiply it by a 1/2 so that the N2 is on the opposite side and there's only 1 mole of N2. So here we go. We'll take it one step at a time. Let's reverse the reaction. So I'm looking right here and I'm rewriting it now. I'm switching. Let me concentrate for a minute. I'm putting 2N2 and 6 H2Os on the opposite side, and I'm putting 4 NH3 and 3 O2s on the other side. Now, that's the reverse. So that means I also have to reverse the enthalpy of the reaction. One more thing, I need to multiply all the coefficients by 1/2. Maybe, let's see. So it's 1/2 times 2. It's 1/2 times 6. It's 1/2 times 4. And it's 1/2 times 3. What is 1/2? I'm going to use my eraser tool now. What's 1/2 times 2? 1. What's 1/2 times 6? 3. Let me clean this up a little bit for you. What's 1/2 times 4? Oops, I don't have the eraser. 2. What's 1/2 times 3? This we're going to leave as 3/2. We do that sometimes, and that's perfectly okay. 3/2. Okay, so that means I need to also remember to multiply or divide 1530 in half. Can I do that in? No, I'll just multiply it by 1/2 right here. Okay, so it's half of 1530, which is 750. 750, 765. I'm going to clean this up. 765. I hope that's right. You can write me if it's not. So positive 765 is the enthalpy of this reversed and halved reaction. Okay, we're almost there. Let's look at the other reaction. Okay, we're going to focus on this 4NO and compare it to this 2NO. Well, it is, NO is a product in both of these, but I need 2 instead of 4NO. So this equation, I don't have to reverse it. I do want to rewrite it, but I do want to divide all the coefficients by 2 or multiply them by 1/2. So let's do that now. So focusing on this equation, I have 4NH3 times 1/2. Let me write it first. 4NH3 and 5 O2s yields 4 NOs and 6 H2Os. And now I'm going to multiply by 1/2. 1/2 times 4, let's do it in our heads, is 2. 1/2 times 5 is 5/2. 1/2 times 4 is 2. 1/2 times 6 is 3. Now, I do have to take 1/2 of this enthalpy. Negative 1170 divided by 2. Okay? What is that? 580, I believe. 85. 585. Write me if that's not what it is. Negative 585. Negative 585. Okay, so let's continue on. We're almost done. Now, when I simplify these two and add it, if I get what I'm trying to solve, then I've solved for the enthalpy of reaction. So let's simplify before we, let's focus for a minute. Both sides have 2 NH3s, and so we can subtract those from both sides. Both sides have 3 H2Os, so we can subtract those from both sides and eliminate them. The only other thing we need to do is combine O2s. Now 5/2 is larger than 3/2. So what I'm going to do is I'm going to subtract the smaller amount, 3/2, from this side of the first modified equation, and I'm going to subtract it from the 5/2. Well, what is 5/2 minus 3/2? Well, it very conveniently is 2/2 or 1 whole O2. Oh, okay, that was a little bit tough. I'll circle it in case you need to review it. And we end up with N2 plus O2 yielding 2NO. How great is that? That looks exactly like what we're trying to solve. Oh, shit, it wasn't recording. Oh, frick. Or maybe it was. False alarm.